Hello everyone, my name is Yui Takeshita and thank you for watching this video on pH measurements and derived carbon dioxide parameters from BGC profiling floats. This video is part of the GO-BGC workshop, and this is meant to be kind of a deeper dive into how pH measurements are made and how the data are adjusted, and then a little bit of specifics on the derived CO2 parameters from these BGC floats. So let's get started. I want to start this talk by showing this animation that shows the location of all of the floats that have been equipped with pH sensors that have been deployed so far. And this data was extracted from the Argo data assembly centers, and the first pH floats were deployed in 2012. And since then, as you can see from the plot, the number of pH profiles from floats per year has been steadily climbing, and in 2020 reached about 6,500 profiles per year. And so as you can see, the coverage and the number of data, number of profiles is increasing, and the first 12 GO-BGC floats were deployed earlier this year, highlighted in the orange box. And so we are funded to deploy a total of 500 profiling floats, all equipped with pH sensors. So we anticipate that the number of pH profiles will continue to increase in the coming years. And so the point of this video and this workshop is to equip you and the community with tools that can take advantage of this coming data set. So this is a quick outline of my talk. I'm going to first talk about the pH sensing technology and the sensor and how the sensor works. I'm going to go into how the sensors are calibrated, and to talk with how we generate science quality data, so how pH data are adjusted and validated, and then also specifics on how derived variables such as DIC, saturation state, and PCO2 are calculated from the float pH data. And I want to point out that most of the data, most of the information in this talk is summarized or can be found in this Argo data management document, processing BGC Argo pH data at the DIC level. So all the specifics on how to calculate different parameters, different constants that are involved in the calculations, as well as MATLAB code and check values are all included in this document. So whoever, if you're interested, go take a look at this document. There's a lot of information in there. So I need to start this talk with just a quick intro on just the marine inorganic carbon system. So the marine inorganic carbon system refers to the carbon dioxide system once it dissolves in seawater. So when CO2 dissolves in seawater, it reacts with water to form the carbonate series, or carbonic acid, bicarbonate, and carbonate. So all of these species combined, and this is what we call the marine inorganic carbon system. And one of the parameters that we can measure in the system is pH, which is defined as the negative log of the hydrogen ion concentration. But the system has 2 degrees of freedom, or in other words, just by knowing one component of the system doesn't fully constrain it. So you need to measure 2 parameters of the marine inorganic carbon system to calculate, which allows you to calculate the other parameters. And the other parameters are total alkalinity, PCO2, dissolved inorganic carbon, and saturation state, or omega. So the most important thing, so in different parameters can be used to study different processes. For example, PCO2 is needed to study air-sea fluxes of CO2. Dissolved inorganic carbon is useful for creating budgets, to study, for example, primary production or anthropogenic carbon inventories. And saturation state can be used to assess ocean acidification potential impacts. And the approach, so as I mentioned before, we need to know at least 2 of these parameters in order to calculate the rest. And the approach, as I will go into more detail later, is that we're going to measure pH directly with the sensor on the profiling float, and then we're going to estimate total alkalinity from an algorithm, a global algorithm, and that's what those 2 parameters on top are what we're going to use to derive the other three parameters, PCO2, DIC, and saturation state. So now that we have that out of the way, let's go into the pH sensor. The pH sensor is based on the Honeywell DuraFET, and then so this was a commercially available pH electrode sold by Honeywell, and the core of the pH sensing principle is the ISFET, or the ion sensitive field effect transistor. And ISFETs have been around for a couple of decades, and many companies produce them, but the Honeywell ISFET showed to be very stable over time. So this is a paper by Martz et al. In 2010 that shows the delta pH, or basically the pH measured by the ISFET to a reference over about 6 months. And as you can see, no significant drift was observed using the Honeywell ISFET. So this trait makes it and it's also low power and solid state. So this makes this a very attractive option to use for autonomous platforms. So this Honeywell ISFET chip was repackaged into a sensor that can withstand high pressure at Mbari, and so this is termed the deep sea DuraFET, and the schematic of the sensor is shown here. And then so this technology was then licensed to Seabird, and now Seabird has made it commercially available for the rest of the community. And then so once this ISFET is packaged into this high pressure tolerant package, then it can then get installed into a profiling float shown on the right here. And there are currently 3 profiling floats that are deployed with pH sensor, and then the Apex, the Navis, and the Provor. And then the BGC Solo 2 float is currently in the final stages of development, and will be deployed in 2021. And so that will be kind of the newest addition to the BGC float array. But all 4 of these floats have the pH sensor integrated into the float end cap, as you can see in the pictures, and they're also integrated into the pumped flow stream of the CTD, and this helps increase the response time of the pH sensor, as well as protect it from light, which is very important, which I will show later. So how does the sensor actually work? And so the deep sea DuraFET is a potentiometric sensor. So what that means is that the sensor measures voltage, and then we convert that voltage to pH. And the voltage is measured between the 2 electrodes in the deep sea DuraFET. The first electrode is the ISFET, shown in the blue here, and then ISFET responds to pH, or changes in hydrogen ion concentration in seawater. And the other electrode is a reference electrode, shown in red here, which is an ion selective electrode for chloride. So this basically, this electrode responds to changes in chloride concentration or salinity in seawater. So the voltage is measured between these two electrodes, and then we convert that to pH. And the equation that we use to convert the voltage to pH is called the Nernst equation, which is shown in the top here. So the VRS pH is the voltage measured by the deep sea DuraFET. And this Nernst equation can basically be broken down into 3 components. So if you imagine, the deep sea DuraFET, the schematic is shown on the left here. It's consistent of the ISFET and the reference electrode, which responds to pH and chloride ion activity. The Nernst equation, the first component is the calibration component, the KTB, and the subscript T and P denotes that this is a function of temperature and pressure. The second term here is the ISFET component, and then this term responds to changes in the activity of hydrogen ion, or closely analogous to the concentration of hydrogen ion, or pH. And then the final term is the contribution from the reference electrode, and this changes the activity of chloride, or essentially changes in salinity. So if you to break this equation down more graphically, you can think of this total measured voltage is represented as white arrow, and is a sum of 3 components. So the calibration coefficient, KTP, the contribution from pH, and then the contribution from chloride or salinity, shown in the 3 arrows. So let's imagine a scenario where now the temperature is kept the same and the salinity is kept the same, shown in the red circles, but pH changes. As you can see, there's more hydrogen ion in solution. So what that does here is that the red arrow, or the reference electrode contribution, stays the same. Since temperature and pressure are the same, KTP stays the same, but the voltage due to the ISFED responding to pH actually changes. So you see an overall change in the measured voltage, and so a change in pH can actually change the measured voltage, which makes sense. We can also observe a change in the overall measured voltage by changing salinity. So now here we have the same pH, but now different salinity shown in the red circles. So again, the blue arrow component, the pH component, the calibration coefficient component stays the same, but the red arrow, or the reference electrode component, changes. And this is due to a change in salinity or change in chloride. So you can also observe a change in the voltage by just changing salinity. You can also see a change in voltage by if pH and the salinity stays the same, but you have a change in temperature or pressure, because the white arrow, or the calibration coefficient, changes, shown in the different lengths of the white arrow. So in order to calibrate this sensor, what we really are looking for is to understand how this white arrow changes as a function of temperature and salinity. And in order to do this, we need to measure the voltage of the sensor in a solution where we know the blue and the red arrow component, or the activity of HCl. And then it turns out the best solution to do this is aqueous HCl, because it's one of the best studied solutions that we know. So we actually do the calibration in about 0.01 molar HCl. And so this is the calibration setup that we use. The pressure chamber is shown on the left, and then this pressure chamber, we can load up to 2 deep sea Durafets on the pressure chamber, and then we can control the pressure and temperature independently of this chamber. So we can now measure the voltage while the sensor is measuring, when the sensor is in 0.01 molar HCl over a wide range of temperature and pressure. So this is what a typical calibration run looks like. The top blue line shows the voltage measured by the sensor. The orange line shows the temperature steps. So we go from about 20 to about 2 Celsius, and then the bottom dark blue line shows the pressure. So so basically the calibration is broken down into kind of a break-in and stress test, where we rapidly ramp pressure and temperature to try to stress the chip, so that we can identify any early failures in the sensor. So once the sensor passes this test, we actually start the calibration cycle, where we temperature and pressure cycle the deep sea Durafet from 0 to 2,000 decibars, and also 20 to 2 Celsius. And we repeat this. And as you can see, so this is a relatively time-consuming process, and this process takes about a week to complete. And we have to do this for every single pH sensor, because the calibration coefficient, or the KTP component, varies strongly from sensor to sensor. So how do we? So what do the KTPs actually look like? So the calibration coefficient, or KTP, is broken down into 3 components. There is a constant term, K0, which is basically defined as the KTP at 0 Celsius and 1 atmosphere. There is a linear temperature term, and the slope is denoted K2. And then there is a pressure term that we denote as F of P, and typically we fit this pressure component using a 6-order polynomial. And so this is what it looks like. And then so on the left, we have KTP plotted on the y-axis as a function of temperature. So you can see it's a very linear relationship, and so the slope of this is K2. On the right, we see an F of P. So this is the pressure component of the pressure component of the calibration coefficient, and then the dashed black line shows the 6-order polynomial fit that we use to quantify F of P. And you can't really see them, but they're different. The F of P is quantified in different temperatures, shown in the different colors, and they're right on top of each other, which denotes that f of p is independent of the temperature, and therefore we can separate the temperature and pressure effects apart. So the last remaining component is K0, which is here, and then and K0 is actually the intercept of temperature of the plot on the left of KTP and temperature, because it's defined as the KTP when it's 0 Celsius. But we can't actually quantify this K0 in HCl because there is an electrode conditioning step that happens once the reference electrode sees a solution, sees seawater. And this is a plot that shows basically the delta pH which is the difference of the deep sea Durafed that first hits seawater versus a reference pH. And as you can see, the pH rapidly drifts by about 0.1 pH units over a course of about 7 to 10 days. And this is because the reference electrode is equilibrating with the bromide ions in seawater, which causes a shift in the potential and therefore a shift in pH. So we need to condition, so once we calibrate the deep sea Durafed in HCl, then we need to let it equilibrate with seawater for about a week before determining the final K0. So once each electrode is conditioned, then we can start to measure K0 in seawater. So this is the setup that we use at MBARI to measure K0, the final step for measuring K0. So the deep sea, you can see the deep sea Durafeds on the right side, and the seawater. And so there's flow cell over the deep sea Durafed that's integrated into the pump of the CTD. So the CTD pump is circulating seawater into a common carboy, which is not shown in this picture. So the same vat of seawater is circulating between multiple deep sea Durafeds, so that way we can calibrate multiple sensors at a time. And then periodically we would take discrete samples and measure pH spectrophotometrically to quantify what the solution pH is, which we need to calculate what K0 is. And an important point to note is that the final K0 step is conducted using the sensor controller that will be deployed on the float. So this setup actually uses a float head that will be integrated onto the profiling flow. And this is important because there are small but significant differences in the voltages that are measured between the boards due to just variability in the ADC. So it's important to pair the controller that will be deployed to the sensor itself. And so what does this process look like? So this is a time series of the pH sensor over a couple of days during the calibration and using the K0 that was quantified in HCl. And then the orange dots now represent the pH measurements from the discrete samples we take from the setup. So you can see that there is quite a big difference, and this is due to the fact that the reference electrode had to be was conditioned in seawater before this final K0 step. So basically what we do is then we calculate the K0 based on the discrete samples that we collect, and then if we recalculate pH using the new K0 in seawater, we get this orange line, and now you can see that the sensor data matches the discrete samples very nicely. So basically the summary of the calibration. So we first have to measure K2 and f of p, which are the temperature and pressure components of the calibration coefficient. Then we need to let it equilibrate in seawater for about a week. And then we finally characterize K0 in seawater by taking discrete samples while the sample is measuring pH, when the sensor is measuring pH. And so we have to do this for every single sensor that is fabricated, and the whole process takes about 3 weeks. It's a very time-consuming process, and this is why one of the reasons why the production for pH sensor is relatively slow, because the calibration just takes so long. And so this is something that we are working on to try to improve and try to speed up. But ultimately, there's not much that we can actually do to speed that up because each step just takes this long. So, yeah. So now once we have the calibration coefficients, we can calculate pH, and the details of this calculations are in this document. that I showed earlier today. But basically, the calculating pH consists of two steps. The first is you calculate pH free, which is equal to the hydrogen ion concentration at in situ temperature and pressure. So it measures pH at whatever temperature and pressure the float is under. And then we convert pH free to pH total at in situ temperature and pressure as well. And we do this because pH total is the most commonly used pH scale in chemical oceanography. So all of the pH that's reported in the Argo data center is reported on the total scale. And I'm just going to show you the equations that are used, and I'm not really going to dwell into the details, but the point I wanted to make in this is that the orange term, the VRS pH, is what the sensor is measured, and all the other terms in this equation that are shown in blue are calculated for temperature, salinity, and pressure. And therefore, in order to calculate pH, you need to know temperature, salinity, and pressure accurately, because all of these terms that go into the calculation are functions of temperature, salinity, and pressure. So that's just something to keep in mind, that to get accurate pH measurements, you also need an accurate CTD. Let's now look at pH data from profiling floats. So as I mentioned, there are two types of deep sea drift at pH sensors that are deployed on floats right now. The first are those that are manufactured at MBARI, and the other one is the one that is commercially available through Seabird. And both of these sensors use the same sensing elements and very, very similar mechanical design, so the performance of the pH sensors are very comparable between the two. However, there is one subtle difference, and that's that I will go into right now. So this is a profile of pH that is collected by Apex floats that are made in collaboration between UW and MBARI. So these are floats that have the MBARI pH sensor, and these floats measure pH at about 70 discrete points in the upper 2,000 meters, and with with changing of vertical resolution. So near the surface, pH is measured approximately every 5 meters, and below 1,000 meters, pH is measured about every 100 meters. For other floats, especially the recent floats that use the continuous profiling CTD, the CP CTDs, that have pH sensors on them, such as Navis floats and the soon BGC Solo 2 floats, these floats collect pH measurements every 2 meters in the upper 1,000 meters of the water column, which is represented by the white line. So this is a subtle difference between the two types of profiling floats, but just something to be aware of. And then but what this leads to sometimes is that there's a mismatch in the pressure grid between the CTD and also biogeochemical sensors, such as pH. And so rather than merging those pressure grids by yourself, if you access the S profiles on the Argo data centers, this merging of the pressure grids have already been done for you. So we highly recommend, if you want to use BGC float data, use the S profiles through the Argo system. And for details about the file structure, please see the data management talk that is available on the workshop website. Final thing I wanted to mention before moving on to the data adjustment section is that the pH sensor, this pH sensor, is very sensitive to light. So this is a profile of pH collected in the upper 200 meters of using a glider in Monterey Bay. But you can see that the initial iteration of the flow cell was semi-transparent. So that means that a lot of sunlight through, and which affected the measurements pretty significantly. So the line is the pH sensor measurements, and the circles represent discrete samples taken alongside of the sensor. So you can see that there is a large positive bias caused by sunlight impacts on the sensor in the upper 10 meters. And so this really highlights the importance of using an opaque flow cell to really shield the pH sensor from sunlight in any deployment. Okay, now moving on to the data adjustment and validation part of this talk. And Data adjustment is a very important part of any BGC float operation because biogeochemical sensors are more prone to sensor drift and calibration offsets than the traditional CTDs on core Argo floats. And therefore, to produce science quality data that the community can use, BGC float data has to be adjusted before it can be used for operational applications or research. And but in order to adjust the data, you first have to understand how a sensor drifts over time. To demonstrate how pH sensors drift on floats, I want to show you some data from a pH float that was deployed off of Hawaii, and this is actually the first pH float that was deployed in 2012. So this is one of the first pH profiles that this float collected, but the sensor drifted low over time. So this profile, as you can see in this profile, so this profile was collected about 2 months after the float deployment, and what you can see is that the sensor drifted pretty much, drifted by a constant pH over the whole profile. So in other words, the pH drifted low at the surface by about the same amount that it drifted low at depth. And then so going back to the calibration coefficients, so how how would we adjust for such a drift? And so if there are any changes in the temperature or the pressure components, so K2 or F of P, then the drift should manifest as a temperature or pressure dependent drift. But what we see in the field is that it is a more or less constant drift in pH. And the only way that such a drift can manifest is if the sensor K0 is drifting. So based on this data, we conclude that the best way to adjust pH sensor data is to adjust the K0 or applying offsets to K0, which more or less manifests as a constant offset or constant drift in pH. So the key is to try to find how much the pH is changing at any part of the water column, and then we just apply. And then we calculate a change in K0 and then apply that for the whole profile. So how do we do that? The approach that we take is similar to how Core Argo adjusts for drift in their salinity data. And we take advantage of the fact that the deep ocean is stable and fairly predictable. So a profiling float makes measurements in the deep ocean for each profile. So if we can predict the conditions in the deep ocean, then we can assess drift, sensor drift throughout the life of the float. And then for Core Argo, there are enough hydrographic and also historical Core Argo float salinity measurements that can be used to create regional climatologies to create this deep reference field that can be used to adjust salinity data. But unfortunately, for BGC floats, we don't have this luxury because, one, there's not enough hydrographic biogeochemical measurements to create these climatologies, nor are there enough historical BGC floats. So we have to take a slightly different approach. To create these deep reference pH fields, we rely on or we use global empirical algorithms such as LIFER and CANYON-B. And these algorithms are trained using the GLODAP V2 data product and are capable of accurately predicting pH throughout the world's oceans, particularly in the deep ocean. So the inputs to these algorithms are temperature, salinity, oxygen, location, depth, and for CANYON-B, date. And so these are all parameters that the float typically measures. And the output of the algorithm is an estimated pH, and with an accuracy of better than about 0.007 at depths below 1,000 meters. And this is fantastic because now we have a way of creating an accurate estimate of pH, in below 1,000 meters, and then so we can use that as a reference then to assess and correct for sensor drift. And so how we do that, we actually do that at 1,500 meters. And so we do that by calculating an anomaly, so a delta pH which is defined as the difference between the estimated pH from the algorithms and the measured pH by the float. And so this anomaly, pH anomaly, represents, so any trends or deviations of delta pH over time should represent sensor drift. And because we make the assumption that the estimated pH from the algorithms are accurate. And so deviations away from that is caused by sensor drift. So how do we actually correct for the sensor drift? To prevent overfitting or overcorrecting the data, we assume that there will be some random variability of this pH anomaly at depth, and so we don't adjust the data until the pH anomalies. We don't adjust the data as long as the pH anomalies are within some sort of confidence bound that is represented by the dashed white lines. And but if the pH anomaly starts to drift outside of this confidence bound, then we will apply a linear correction for the section of the data that started to drift, which is represented in the blue arrow there. So then, so we can linearly detrend this data and then apply adjust the sensor data using this pH anomaly. And it's not uncommon to see jumps in the data like this. This can just be due to a variety of different reasons. For example, something could have just gotten stuck on the sensor surface. And so to accommodate for jumps in the data set, we use a piecewise linear regression correction. So we apply linear corrections for different sections of the float time series, represented by the two blue arrows. So so that way, if there's any jumps in the data like this, we can actually correct for those patterns. Okay, so now I mentioned that there were two algorithms that exist, LIFER and CANYON-B. So you might be wondering, does it matter which one we use? And the answer is, yeah, it kind of does matter, and that's because LIFER is an algorithm that's consistent with pH measured spectrophotometrically using purified M-cresol purple, whereas CANYON-B produces a pH that is consistent with pH that is calculated from alkalinity and DIC. And unfortunately, these two pHs are not internally consistent. So this is a plot by Carter et al. In 2018 that shows that there is a pH-dependent trend between the pH that is measured directly using spectrophotometric approaches and pH as calculated using alkalinity and DIC. And this plot here is created from data that's been adjusted using the GO-BGC protocol. So that, for alkalinity and DIC, they should be an internally consistent data product. So you can see that so it will start to matter because depending on if you use LIFER or CANYON-B, you will have a pH-dependent difference between the two algorithms. So, so which one should we use? Right? So should we use the algorithm that is consistent with pH spec or pH alkalinity and DIC? And we have chosen to correct for correct the algorithm that's consistent with pH spec. Based on this paper, Takeshita et al. In 2020, where we demonstrated that spectrophotometric pH and pH measured by the ISFET, or the pH sensor that's equipped on the profiling floats, are consistent. So this plot shows the difference between the pH spec and pH ISFET over a range of pH, and the different colors represent different electrodes that we tested. And the dashed red line is the pH-dependent error that we saw in the previous plot by Carter et al. In 2018. So this study, we basically demonstrated that the pH the pH measured by the float is consistent with pH spec, and therefore we have decided to correct pH on profiling floats based on LIFER, which is consistent with pH spec. But if you want to use CANYON-B for whatever reason, you can kind of correct for this pH-dependent discrepancy by applying this linear adjustment to the pH output from CANYON-B. And so the slope and the intercept, the negative 0.0404 and the 0.3168, comes from the linear regression from the plot in Carter et al. In 2018 that I showed previously. So you can kind of convert between pH Canyon B, which is pH, which is consistent with pH calculated from alkylating DIC, to pH quote unquote spec. But I really want to emphasize that if you want to apply this adjustment, please use this with caution, because this really is an empirical correction, and we don't know the reason why this pH discrepancy exists in the first place. And then so such adjustments, the coefficients are subject to change with future research. And also we really want to first understand the cause of this discrepancy, so that we are not, we can actually make a mechanistic correction rather than just an empirical correction. So, but this is an active area of research, so hopefully we will find the answer in the next couple of years. Okay, so how does the adjusted data, pH data from the floats, look based on these algorithms? So one way we can look at that is look at the magnitude of the offset that needed to be applied to the sensor data based on these algorithms. So this histogram shows the first adjustment that were made on the floats, shown in blue, and the second adjustment that were made to the floats, shown in red. And so remember, the adjustments are made in a piecewise manner, so different, multiple adjustments are typically made over the life of a float. So you can see that the first adjustment is skewed low, and it's not uncommon to see adjustments larger than 0.1, as you can see from the the values on the lower left of this plot. And then, but the second adjustment the magnitude tends to be smaller, and more or less normally distributed around 0, with the standard deviation about plus minus 0.05. And so this first large, this large offset that needed to be applied on the first adjustment is really driven by earlier iterations of the pH sensor. So this is a plot that shows the first pH adjustment that has to be made over the past 6, divided up by the year that the float was deployed. So you can see that the first 2 years, 2014 and 2015, most of the floats had to be adjusted by about 0.1, and this was because these sensors were not properly equilibrated with seawater prior to deployment, and we also made some minor mechanical improvements to the sensor over time. So you can see that after 2015, so starting in 2016, the adjustment that has to be made to pH unit, the pH sensors, is significantly smaller than in the previous iteration, and the variability of this offset is improving over time. As you can see, the error bars are decreasing, from 2016 to 2020. So this is good news. That means that the sensor performance is improving over time. And a similar story can be seen with the drift for these pH sensors as well. So this histogram shows the drift adjustment that needs to be applied in the first year of a float's life versus the second year of the float's life. And you can see that the magnitude of the drift tends to be larger in the first year compared to the second year. And then the distribution of the drift in year 2 is centered around 0. And so it also seems like once the sensor kind of settles in, there's maybe a settling in period after it's deployed, and then after that the drift tends to significantly slow down over time, which is great. Okay, so after all these adjustments are made to the data, how good is the pH sensor data? So one way we can validate the adjustment is by comparing float data to shipboard data. So the SOCON project has done this over the past 6 years. So they have collected discrete pH samples for the majority of the 200 floats that they have deployed over the past 5 years. So this is a plot that shows bottle pH on the x-axis and float pH on the y-axis after it has been adjusted using the method that I mentioned before. And you can see that there's excellent agreement between the discrete samples and the float pH, with a median residual of negative 0.002 plus or minus 0.015. And we make the assumption that the variability a part of the variability is actually due to the spatial temporal discrepancy between when the float collected the pH measurement versus when the discrete samples were collected. And this is because the float surfaces approximately 18 hours after it is deployed, and during that time it can drift, kilometers. So the discrete samples and the float measurements can be separated by 18 hours and many kilometers. So we would expect some sort of just difference due to this spatial temporal variability of the ocean. And if you make the assumption that about half of this variability is the variability between the float pH and the bottle pH is due to the spatial temporal discrepancy, we can conclude that the accuracy of the pH measurements from the float is around 0.007 or so. So that comparison was made on the first profile of the float, but we also want to continue to evaluate the performance of the sensor throughout the float's lifetime. And then so the approach that we have taken to do this is to compare crossover data between float profiles and GO-BGC stations. So we define a crossover as any profiles that a float makes within 20 kilometers of a GO-BGC station. And then we can compare the two values. And so here's a plot that shows the comparisons, and that only include data below 300 meters. And the plot shows the difference between GO-BGC pH and the float pH. And the top panel shows comparisons of float data within the first 6 months of the float's life. And the bottom plot shows the float data after it has been deployed for at least 2 years. And the one thing that you can notice is that on average, the GO-BGC pH data is a little bit higher than the float pH by about 0.025. And we argue that this is not due to sensor error, but in fact, it actually represents an acidification signal between the GO-BGC data and the float data. So on average, the GO-BGC data is about 20 years older than the float data. And assuming the canonical acidification rate of about 0.001 pH per year, this difference between GO-BGC pH and float pH is it makes sense. It's on the right. It's about the right magnitude. So we argue that this mean offset doesn't indicate any sensor error, but in fact it is real differences between the GO-BGC data and the float data. But you can see that the variability around this mean is not significantly different between data in the first 6 months of the float's life versus after 2 years. So this also suggests that the float data doesn't degrade over time. So that's very good news. Okay, so now moving on to the derived carbon dioxide parameters section of this talk. So as I mentioned before, we can combine pH measurements. We can use the pH measurements from the floats to derive other carbon dioxide parameters such as DIC, PCO2, and saturation state. And we do this by combining pH measurements from the float with another parameter, which is total alkalinity. So we estimate alkalinity from float measurements using, once again, these global empirical algorithms. For in this case, to estimate alkalinity, we use Lyre or Canyon B. So the inputs to these algorithms are the same: temperature, salinity, oxygen location, depth, and date. And the output is estimated alkalinity with an accuracy of about plus or minus 6 micromole per kilogram globally. So once we have an estimated alkalinity, we can combine that with the measured pH from the float and use a program such as CO2 sys with inputs of pH, the measured pH, and estimated alkalinity to calculate DIC, saturation state, and PCO2. So that's the approach that we take. So what are the uncertainties associated with these derived parameters? And I'm going to first talk about DIC and saturation state, and then go into PCO2 for reasons that will become clear in just a second. So this plot on the left shows the uncertainty in the derived DIC as a function of DIC using a Monte Carlo approach. And then the uncertainties that went into this simulation is plus or minus 7 micromole per kilogram for alkalinity, plus or minus 0.01 for pH, and plus or minus 50% of the nutrient concentrations of phosphate and silicate. So you can see the uncertainty of DIC actually remains relatively constant. It's within 1 micromole per kilogram over a very large range of DIC, so ranging from about 1900 near the surface to about 2400 at depth. And so what this basically means is that the uncertainty in the derived DIC is largely dominated by the uncertainty in the estimated alkalinity from the algorithms, and the uncertainty in pH has a noticeable but less significant impact on the overall uncertainty. So more or less, you can kind of think about the uncertainty of DIC is equal to the uncertainty in the estimated alkalinity. And that's, that's an approximation, but a pretty good one. The uncertainty for the saturation state is a little bit different. So the plot on the right shows the uncertainty for the derived saturation state as a function of saturation state. So you can see that there's a clear dependency, the clear dependency on saturation state or pH. So, and in fact, the uncertainty for saturation state is lower at lower pH. And so and it's about 2% of the saturation state. And I would like to note that the climate quality target for saturation state set by the Global Ocean Acidification Network is about 1%, and then the uncertainty associated with these derived saturation state from floats is about 2%. So we're pretty close to meeting this climate quality target from floats. So we can validate these derived measurements using the same approach by comparing discrete samples collected at the time of float deployment. And this plot shows the bottle DIC on the x-axis and the float DIC on the y-axis. The solid line is the 1-to-1 and the dashed line is the model 2 regression. And the mean residual between these two measurements is -1 plus or minus 7.5 micromole per kilogram. And so that uncertainty, the 7.5 micromole per kilogram, is in pretty good agreement with the uncertainty for the alkalinity, which is about plus or minus 6. So, that Monte Carlo, this kind of top-down validation agrees with the Monte Carlo simulation pretty well. Okay, so now moving on to PCO2. So the uncertainty for PCO2 has been studied in much more detail than DIC or saturation state. So Nancy Williams has a very nice paper in 2017 that did a very thorough bottom-up uncertainty analysis for the derived PCO2. And so this plot, I'm not going to go into the details, but basically every single arrow that's shown in this diagram here represents a source of uncertainty or source of uncertainty for the overall estimated PCO2. And so Nancy, she quantified most of these sources of uncertainty for each arrow and then added it all up and concluded that the uncertainty for PCO2 from floats is about plus or minus 11 microatmospheres at 400 microatmosphere background PCO2. And it's important to define the uncertainty with respect to a background PCO2 because, like saturation state, the uncertainty in PCO2 is highly dependent on the background PCO2. So in terms of percentage, it ranges from about 2.5 to 2.1%, and the uncertainty actually goes, in terms of percentage, goes down as you go to higher PCO2. But since the magnitude or the background PCO2 is higher, so 1,000 microatmospheres, 2% of that is 40 microatmospheres. So the absolute uncertainty in units of microatmospheres increases as PCO2 increases. So so this is just a note of caution when thinking about uncertainty related to PCO2. So you have to take into account what the background PCO2 is as well. So there is also another complication with PCO2 in that, like the pH, we are kind of running into an internal inconsistency problem with PCO2 as well. And so this plot this shows the difference in PCO2 between directly measured PCO2 and calculated PCO2. And the points in pink shows PCO2 that's calculated from directly measured pH using spectrophotometric approaches using purified M-cresol purple and alkalinity. And this data comes from the GOMAC2 cruise in the Gulf of Mexico and the east coast of the United States, presented in Patsavas et al. In 2015. But if you compare the PCO2 that is calculated from alkalinity and DIC, then we see a very different pattern. And so the blue dots show the PCO2 that's calculated from alkalinity and DIC from average from 8 GLODAP cruises. So the alkalinity and DIC has been adjusted using crossover analyses. And you can see that the PCO2 that's derived from pH, shown in pink, has a very distinct PCO2 dependent difference between directly measured pH and calculated, whereas the PCO2 that's calculated from alkalinity and DIC agree much better to the directly measured PCO2 over a large range of PCO2, and in fact it agrees to better than plus or minus 5 microatmospheres to at least 1,000 PCO2. So what this plot basically shows is that PCO2 derived from pH measurements, spectrophotometric pH measurements, has a PCO2 dependent error in it. And remember, since the pH in pH spec and the pH from floats are internally consistent, the PCO2 estimated from floats would follow the pattern of these pink dots. And so in order to, so we need to make an additional adjustment to the pH data so that the estimated PCO2 is consistent with consistent with the blue dots, which is also consistent with the directly measured PCO2. So we make this adjustment by going back to this plot presented in Carter et al. In 2018. And so we use this relationship. So this plot shows the difference between directly measured pH and pH calculated from alkalinity and DIC. And since we, from the previous plot, we think that PCO2 is consistent with, with alkalinity and DIC, our approach is to adjust the pH sensor data so that it is consistent with alkalinity and DIC. So we use this relationship in Carter et al. To apply an adjustment so that pH float is consistent with pH alkalinity and DIC at 1,500 meters. So this is the place that that depth is where we adjust for sensor drift. So depending on what the pH level was at 1,500 meters, we use this linear relationship shown in the black line and make that correction to the float pH, an additional correction to the float pH measurement, so that now in essence we have made the pH measurement from the float, quote unquote, that is consistent with alkalinity and DIC. So sorry, I understand this is very confusing, but so we have decided to make this additional adjustment. So kind of looking at it schematically, so this is the the block diagram for how to estimate the drive parameters. But given this knowledge that PCO2 is a little bit different than the other values, so we use directly measured pH to drive DIC in saturation state. But when we drive PCO2, we apply an additional correction to the measured pH so that the pH is actually consistent with pH calculated from alkalinity and DIC when and only when we drive PCO2. So I hope this block diagram is helpful when you're using these drive parameters, and and hopefully we'll explain why. Hopefully you understand why we have decided to make this additional correction only for PCO2. And again, I would like to emphasize, we completely recognize that this is an empirical correction, and we are working hard to try to figure out what's causing this discrepancy so we can fix it at the mechanistic or thermodynamic level, so that we don't have to apply any of these additional corrections. And stay tuned, I guess. Okay, so I want to finish this talk coming back to this animation that I showed you at the beginning of the talk. And I just want to emphasize that the number of pH profiles are steadily increasing over time, and they will continue to increase over the next many years. And so we hopefully from this talk you've learned how these pH measurements are made and what kind of adjustments they are made, to account for sensor drift and also the derived parameters. And so all of this data is publicly available in real time on the Argo data assembly centers, and also on the FloatViz portals for the derived parameters. And so for details, please look at the data management talk. But this data set is available and ready to be used by anyone. So I hope that you have learned something useful in this talk that allows you to take advantage of this data set. And thank you very much for your time, and thank you very much for your attention.